Good morning, good afternoon, good evening from wherever you are. It's good morning in Melbourne, and welcome to our first Matrix Online Seminar in 2021. We're very pleased to have Andrei Okounkov from Columbia University present this seminar. I don't think Andrei needs a lot of introduction for the audience here. Suffice to say that he received the Fields Medal in 2006 for bridging the gaps between probability, algebraic geometry, and representation theory. Andrei has been a strong supporter of Matrix in the past, so it's a particular pleasure that he's now able to speak in our online seminar. All right, over to you. Before I forget, if people have questions, please put them in through the Q&A function at the bottom of your screen. So we'll not use the chat, but the Q&A, and the questions will be addressed at the end of the talk. Over to you, Andrei.
Thanks, Jan. So let me start the screen sharing, and here it is. All right, thanks. It's a great honor to be addressing you all this evening, New York time, this morning, Melbourne time. It's yes, I wish I could be there. I could be there in person, but instead it's through Zoom. But anyway, it's a pleasure. Anyway, and then so as we go through the slides, slides is a mixture of kind of elementary math and maybe not so elementary math. So as we go through them, you may want to maybe scroll back and forth through. I've put a link to the. There's also on the I think on the Matrix webpage there's a link to the slides. Especially if we this is a 45-minute talk, and if we don't get to the punchline in the end, it's all right. In some sense, the punchline is in some sense written behind me, so you've seen it already. And if we run out of time and not get through kind of more technical justification of that'd be, you know, you can look in the notes and see what it says. And so so then okay, now progressing, now I have to use the right copy. Yeah. So in some sense, a linear, we will be from purely math, from pure kind of analytical point, we will be solving extremely simple equation. These are linear Q difference equation with regular singularities, and if they'll be slightly multivariate for us, but it's not a big deal. If we were talking about a univariate such equation, the univariate such equation has the form written, where if I have a f is unknown vector valued or matrix valued function, and if I shift the argument of that function by q, then it gets multiplied by some matrix m. And the statement that this is equation with regular singularity is that first of all, this m is a matrix of rational functions, some variable z, and also its values at 0 and 1 are regular and invertible, so they take values in GL. And in the rest of the talk, we'll take q to be a complex number of absolute value less than 1. So that's you can also take it more than 1, but absolute value equal to 1, that's something else which we're not going to be addressing in this talk. So this is, I hope this is you've seen something like this before, but if you haven't, this is entirely parallels. So this is entirely parallels some questions, some issues in the ordinary differential equation, and as we will see in a second. And so now, if I look at this equation formally, when we look at equations, so maybe I can try to move my cursor here. So if I look at this equation, then formally it's solved by this infinite product. And the difference between the differential equation and the Q difference equation is that this difference product actually converges if m of 0 is 1. So for instance, if I take what's known as Q gamma function, if I want to write infinite product for the ordinary gamma function, then I will need that requires certain regularization. But an infinite product for the Q gamma function is just a converging infinite product. The product written there, it's that if absolute value of Q is less than 1, this converges for all values of Z. And so that's yeah. So that's so this function solves a scalar Q difference equation. And then another example is the Q hypergeometric function, which is written here. So this is like the ordinary hypergeometric function, except where the ordinary hypergeometric function, if you've seen that, if you've ever seen a formula for an ordinary hypergeometric function that has this kind of full factorial powers, or whatever factorial powers of the variable, where you get a x times x plus 1 times x plus 2 and so on and so forth. The analog of this in Q world are this Q factorial powers, where when you take 1 minus x, 1 minus qx, and so on and so forth, or the ratio of two, or you can define both you can define both of the special functions in the same kind of way as the ratio of two gamma functions. So if you take the ratio of two gamma functions, you get ordinary gamma function will give you ordinary factorial powers, and the Q gamma function will give you this Q factorial powers. And if you form a series like that, that would be a series satisfying a second order Q difference equation in the variable z. And if you're not gonna get, if there's something you want to get out of this talk, maybe you're supposed to forget everything, but maybe you should remember that there's something nice about solutions of certain particular Q difference equation. And here's an example. This is a function which is, I would say that this is given by a beautiful series, and we'll be also similarly talking about functions given by beautiful integrals. And the Q difference world, the difference between series and integral kind of disappears. So in the ordinary, we mathematically distinguish series and integrals, but in the Q difference world, it's pretty much the same. And so anyway, so there's some beautiful formulas for solution of Q difference equations, and beauty, of course, subjective, but if you want to remember something I would consider a beautiful formula, here's an example. Anyway, this is at least for those of you who stayed with me for the first 3 transparencies, maybe this is something to take away from the slide. And now an abstract theory, if you want to know existence and uniqueness of solutions holomorphic in some punctured neighborhood of unit circle, that entirely parallels the differential story. And Nalini asked in questions about resonance condition, and these are exactly parallel resonance conditions for between ordinary differential equations and the Q difference equation. This means this is a question whether you're going to be in powers of z, or you're going to also involve logs of z and so forth. But that's entirely parallel question. One big difference between Q difference equations and differential equations is that there is a lot of Q difference constants. So if I write Q difference equations, or differential or difference equation, that's an equation which is not linear over all functions, but linear over constant functions. And in the differential world, constant functions were just constants. Whereas in the Q difference world, the constant functions are the functions that don't change their value as I shift the argument by Q. That is to say, they're functions on their meromorphic function on an elliptic curve. The elliptic curve being the quotient of C star by Q, and of course there's a lot of it's a field of transcendence degree 1. There's a lot of elliptic functions, and everything we do is linear over those functions. It will be kind of important. And also another interesting point about Q difference equations is that while in solution of differential equation we have to rely on some theorems to say that the solution is going to be analytic, analytic in some domain. We have to use analytic attenuation. In Q difference situation, the analytic attenuation is automatic. It's just like with the gamma function. When we teach about the gamma function, we prove it's analytic for sufficiently large when the argument has a sufficiently positive real part. But then by the difference equation itself, it then becomes it gives a meromorphic attenuation to the whole complex plane. Same with Q difference equations. Once we have solution in some punctured neighborhood of 0, then just the difference equation itself, and you get automatic analytic continuation everywhere. Okay, so that's okay, here's some technical thing I need to adjust. So now going forward. So linear Q difference equation, they're not kind of esoteric subject, that's a very concrete subject, and they do appear in what I consider kind of deep and very important branches of mathematical physics. Maybe most of you would be familiar with two-dimensional lattice models, where appearing of difference equation has somehow exactly parallels the fact that what in the continuum is governed by differential equation, on the lattice level before we go to the continuum is described by difference equation. And examples of, and also it appear in some 2+1 dimensional situation. That will be the bulk of our discussion. And they're very important examples. There are McDonald Q difference equation, and then there's also min, and then which intersect the two kind of large families and the many more families. There are the sort of McDonald equations, and there's also the quantum Knizhnik-Zamolodchikov equation. That's another very important class of Q difference, of linear Q difference equation of the kind we consider here. And I'm not going to write this equation down today in this lecture. It's just it will be a separate interesting lecture to write down these equations, and since writing them down requires a lot of representation theory, I think it's best if I just leave that box unopened today. And this is really the subject, and Jan, who introduced me, he's for those of you who are in Australia, you should ask him. He would be, I hope he would be able to. Well, anyway, it's a deep and important subject, and going back to what we want to do is we want to know in application, what you need to know very often is a special value of the solution, or a transport. Means you start with a solution, you ask for what does it behave, or means if you define solution, say near z equals 0, you'd like to know what the solution is going to be asymptotic to net 0 from infinity, and that's a problem. So Birkhoff, this particular kind of transport problem, actually Birkhoff calls monodrome. So this is something called monodrome in the Q difference world, and for a good reason. But for all these applications, it's great. So if I have an equation and I want to know it's monodrome or special value, those are the same kind of questions. It means I have solution normalized at maybe at near z equals 0. I'd like to compute its value at some different point. Then it's great if I have a formula, right? So this, I think this is and what would be this talk would be about having formulas for solutions. So okay, so slightly. So it's a slightly. I mean, the talk is on a slightly old-fashioned subject. We're solving linear Q difference equation, and we're looking for a formula for a solution. So that's. But as old-fashioned as it sounds, it has some intersection with more with other branches of mathematics. So now I keep advancing, trying to advance slide on a different. So now in the differential case, one is very happy if let's say F is the fundamental. Let's say F is the fundamental matrix of the fundamental solution. One is very happy if one can write the solution as in an integral form. Means if you want the ijth matrix element of the matrix, then you'd like it to be the integral over ith form over jth cycle, where the ith form is what is it? You introduce some new integration variables, maybe call it y1 to yn. I mean, you have n of them, and since you have new variables, you have to kill them. Means you have to integrate them out. So there has to be a cycle of integration of that same dimension n, and you integrate that form over the cycle. And maybe more kind of what's the word? More geometrically, this means there's some other algebraic variety. You know, I mean, this y's are coordinate in some other algebraic variety that depends on your variable z. And then the form well, the form is a form on that algebraic variety that has n holomorphic and 0 anti-holomorphic differentials. So it's a form of type n equals 0, n 0, and then there's a cycle integration of dimension n. So there's an element of h n 0, and there's cycle of integration gamma I in nth homology group, and so you're pairing some element in cohomology with some element in homology. And in a more pictorial way, it means you exhibit your differential equation as something called the Gauss-Manin connection of a family of algebraic varieties. Namely, you have a family of algebraic varieties depending on Z, and then you want to know how the integrals of holomorphic forms over cycles change as I vary the parameter Z of that family, and that's the standard. What's known, this means my connection is what's known the Gauss-Manin connection. Means the connection describes that how the transport of homology and cohomology in a family of well, in general, in this case, algebraic varieties. And I should warn you that not all connections, for very basic reasons, not all connections are Gauss-Manin connections. You shouldn't be. You shouldn't be. You will not be able to solve a general differential equation in this form, for the simple reason that, for instance, if something is a Gauss-Manin connection, this really pins down the monodromy, because, for instance, the way I've written, if omega is really a holomorphic form, then the monodromy of my connection, that is really the monodromy of my family of I have a family of algebraic variety, I have homology group, and really monodromy of cycle, that's my monodromy of my connection. So in particular, in some basis, my monodromy should be defined over Z, which is of course it's not going to be the case for general monodromy, some transcendental thing, and there's no basis on which to define over Z. So that's a simple argument why not every connection is a Gauss-Manin connection. And so an example slightly generalizing the notion, for the hypergeometric equation, if I want to write the Euler integral for the hypergeometric equation in this form, what do? I take my family B complex line minus 3 points, and these 3 points I take 0, 1, and the other point is Z inverse, which is so I have a family where it's a C minus 3 points, 2 points stay put and one of them moves, and then my differential form is the form written here, and this is not exactly a single valued function. You see something raised to fractional or complex powers here, but that's okay, because for this Gauss-Manin thing, the form doesn't need to be by itself, doesn't need to be a holomorphic function. It can be a solution of a simpler differential equation. In this case, is a solution of a scalar differential equation, because that function here, although y to the complex power is not exactly a holomorphic function, but it solves a differential equation where the matrix is holomorphic. So, and generalizing this example, a lot of very, very useful functions are written in terms of integrals of some linear forms raised to complex powers, and that's and in which case the corresponding variety y is just complex space in which you remove all these hyperplanes. That's a generalization of this example, and maybe so. This is all these functions perhaps deserve to be called hypergeometric functions. That's and this is, as I said, this is not, of course, not all solutions of differential equation are hypergeometric functions, for the reasons that these guys have, for example, their monodromy is something very well defined. I mean, it's not defined over integers, but defined over like things which contain things like exponential of 2 pi, constants like defined over a certain specific thing, and that's and so that's not all equations hypergeometric, but this is a very, very large world of things where a lot of useful functions appear, and in particular all functions that we'll be discussing will be Q generalizations of this sort of expression. And in fact, right, before we go to Q generalization, we will draw a lesson from what we discussed here, that we started with a difference equation, which was just written in some vector space. It's some vector space Cn, has no name. But in fact, it does have a name, that vector space. If we want to solve it by along the lines how we're going to solve it today, that that vector space does have a name, and that it is in fact, it's some homology or cohomology group of some algebraic variety. But in the story we're going to discuss today, in fact, this will be something else. Will be some other algebraic variety X, which is related to Y via some sort of some interesting transformation, and then we will be talking about the cohomology. But in fact, we're talking about K theory of X, which is kind of like cohomology, but even better in many respects. And so what's it going to be? So first of all, when we take products of linear forms raised to complex powers, there is a very straightforward generalization of that to the Q world. Namely, you should take where you previously had linear forms raised to complex powers. You should be thinking that the analog of a linear form is a monomial, or maybe monomial times a constant in some variables, and then you take the ratio of two gamma functions. So the ratio of two gamma functions with a little bit of a shift, the way written here. So maybe I'll point it here, but the ratio of two gamma functions says here lambda is the analog of L, and the ratio of A and B is the analog of C. So this fractional powers become the ratio of two gamma functions in the Q different worlds. And once you have that, then of course it's clear that you should, instead of having a C minus the union of hyperplane, which was Y before, we make Y to be the torus in which you remove the poles. And that would be means I have Y, it's a torus in which I remove a translate. So the poles in the gamma functions are some translates of subtorus of codimension 1, and so I take my torus and I take remove a translate. I have some torus of subtorus of codimension 1. I take its shift, and a certain shift, which is in this case shift by A, and then I further remove it, always translates by Q, that sort of thing. And then this would be the first kind of leap of faith. That is that, well, not of faith, but the first thing is that we can also, right, maybe okay, this will be not, we're not going to make any dramatic changes now. I'll just point out that sometimes this arrangement of subtori, which I'll just keep referred to this. I mean, if you take the logs, then you get something like arrangement of take a log and subtorus, then there'll be a linear picture which is depicted here. And then sometimes, very often, this picture have a certain Weyl group symmetry, so you might as well pass to the quotient by a Weyl group. And the Weyl group here is just a finite group. I don't need it to be generated by reflection or anything like that. So, I mean, it might be generated by reflection, but there's some symmetry. You might as well go to the quotient. It's just a little point. And in particular, if that finite group actually happens to be a Weyl group of some group G, which actually is a finite group generated by reflection, then this quotient of a torus by the Weyl group, this is the conjugacy classes. This is a set of conjugacy classes in my group, or some simple conjugacy classes in my group, and what it is the spectrum of the representation ring of the group. Right? So, I mean, representation ring is generated by the characters. Those are functions constants on the conjugacy classes. And this is, if I take the spectrum of that ring, that's just the torus module, the Weyl group. So then I get everything sits inside the spectrum of representation ring of my group, of some group G, and that representation ring of some group G is also called the equivalent K theory of a point. Because what is K theory? K theory, equivalent K theory is the ring formed by bundles with respect to the operation of direct sum and tensor product. Equivalent K theory is the same thing when you have bundles with an action of a group. And so in particular, if the underlying space is the point, then it's just a ring of representation. So this makes sense. This is why it's called the current K theory of a point. And I should, while the slide, I want to point out that we have very specific Y's here. It's a torus minus some subtorus, and the exploration of the kind of the exploration of some sort of Gauss-Mannian type world outside of this family of varieties is it's in complete infancy right now, but very exciting infancy. So because it has to do with prismatic homology and other amazing things, and so it's by all means worth exploring. But this will not be this is not the direction which we're going, because in our case it's something that we're going to. So anyway, we're going to restrict to this case. I mean, the case of our varieties Y being complements of the shift of subtor inside of some ambient torus. Okay. And so finally, the integrals. So that's my main formula written behind me. Those are the integrals we're going to study. Is the following: is that we take so this will be the general shape for the solution. So if we have a fundamental solution, it's a matrix, and so we take a matrix coefficient, means we have two elements in the space in which the matrix, whether the matrix acts, alpha and beta. And what we're going to do, we're going to take this alpha and beta to some functions on of the variables Y, the integration variables, and whatever variables and dots stand for whatever variables. And dots in F and G stand for whatever variables I had in my original equation. So Y are the dummy integration variables. They're going to go out, but also I had some variables in, I started with some variables in the equation, and so I need a linear map from my space to functions in dummy integration variables, and then I take, and there's some integration weight, which is a ratio of Q gamma function. And then I take integral over just the compact torus, all absolute values of Y equals 1. So that's kind of the main formula. And where, as I said, alpha goes to F sub alpha and beta goes to G sub beta are certain linear maps. Their targets are F of alpha is a Laurent polynomial, and G sub beta is a theta function. Theta function means that if I shift the arguments by Q, then I get a function of the same kind times an automorphism factor. So it means it's a section of some line bundle all on the quotient by translation by Q. So this means I take a bunch of all my Y's lived in some torus, and I move, and I mod this out by translation by Q. It means I get the thing which is like a product of elliptic curves. So the product of the elliptic curves, which are each elliptic curve is C star mod Q. And if I further had some file group symmetry, then I get the product of elliptic curves mod W, and so that's equivalent elliptic homology of a point. And I see Nor is on this call, and so you can ask, by all means, you should ask Nor about what this theory is about, and that's it's a beautiful theory. We'll only touch on it very slightly. I have no idea what my camera is doing. It's I think it's due to the fading light. Eventually, hopefully, it'll come back, but hopefully, it'll come back in a second. Okay, here. So so now I want to point out when we started out. When we wanted to compute the ith chase matrix element of the fundamental solution, we integrated ith forms over J's cycle, if you remember what was happening. But now I said, well, we can instead integrate the product of functions. And the reason we can't do it is because we have so many Q constants, Q difference constants. We have a world of elliptic functions, many Q difference constants. Means there's a lot of things we can introduce without changing the equation satisfied, because the equation satisfied Q difference equation satisfied by an integral like this depends on the equation satisfied by the integrand. But if I multiply by something elliptic under the integral, it's like having some kind of measure of integration that's invariant under sheaf. And if I have this much freedom, then I can replace the choice of a choice of counter of integration is the same as the choice of measure of integration. But I have so many functions that I can introduce without changing the equation. Means I can adjust the measure of integration to be anything I want. So this is, I'm slightly, maybe it's only a plausible statement, not a proof, but it is true that if we're going to solve the equation, then in fact it's enough, instead of having a function in a contour, we're going to have two functions, and one of them is elliptic. That's the change from what we had before, and the contour stays the same, just the real torus, or the compact torus. And so once you write this equation like this, so the constant equation like this, then in principle, if I write you, I have the equation behind me, so it's just, you can read it. If I write any integral of this form, this will solve some Q difference equation, and but to compute what equation it will solve, this is what algorithm, in some sense, it's algorithmically extremely tedious, because it's like, in some sense, you compute quote unquote direct image of Q difference module, and it's easier said than done, because it's complicated, and it's hard work, and a lot of smart people over the years analyzed very special cases of that, and there's a long list of people. I apologize to anybody who's missing on this list, and I mean, there are many people missing on the list, and I want to express my appreciation and whatever, what's the word? The admiration for the dedication of people who were able to actually kind of analyze this. I mean, not very direct, still developing a lot of mathematical theory, analyze this and prove that some expression like that solves, say, Knizhnik-Zamolodchikov equation, certainly solved. And the reason I wrote Reshetikhin himself is because Frenkel and Reshetikhin were the ones who introduced the quantum Knizhnik-Zamolodchikov equation, and so therefore, there's some original work about this Q integral solution done by Reshetikhin himself. That's why he appears there with himself. And there is a point here in this thing which I want to emphasize. There's a certain interpolation problem here that plays a role. Namely, as you compute this integral, what you're going to do? You're going to, if you want to compute the difference equation satisfied by an integral like this, well, you will have to use the difference equation for the integrand, and then you have to you move yi's around, but that means your contour moves and it goes on the other side of a certain pole. Then you have to move the contour back, pick up the residue. And so as you pick up the residue, you will have to know some interpolation properties this function f and g may possess at the residues of the integral. So there's some interesting set formed by kind of so as you move this integration in y's, there's a very interesting closed set formed by the deepest residues in y's of the gamma function. This is the measure of integration becomes something kind of zero-dimensional supported at points, so not right, but kind of the deepest residues in y, zero-dimensional in y, and then it depends on all other variables. And you need to know what this function f of alpha, g of beta, what sort of values can they take there, and that's the interpolation problem, and we'll come to that from a slightly different angle in a few slides. But to analyze this integral, we will consider what appears as a completely different object. Namely, there will be some absolutely different variety x, and what this variety x is some algebraic symplectic reduction. Algebraic symplectic reduction means that you have some representation of your group M, and then we consider you have some group G, to which we briefly alluded before, but now imagine we have some group G, and it has some representation M, and then we consider cotangent bundle of that representation. It will be a linear, now symplectic representation. As being a symplectic representation, have a moment map to the dual of the Lie algebra, and then first of all you equate that moment map to 0, and then you take the quotient of the remaining thing by the group G. So this is like the symplectic reduction, but now done in this in the context of algebraic groups and linear representations. And the GIT quotient that you take at the end by the G means you throw out all the unstable points, so you go to the open stable locus, and then also you impose the moment map equation. But the stability condition, so the stability condition you can also impose using the real moment map equation, and then you mod out by the compact group, and the totality of the real moment map equation and the holomorphic or complex moment map equation that we're talking about here, this you can write as maybe summarized as being a critical locus of a certain function. And the reason I'm saying is because that's how it appears in the kind of theoretical physics we'll be talking about, or we should be talking about this in this talk, is that when you have there becomes something called the Higgs branch of vacuum in a certain gauge theory. What's a Higgs branch of vacuum? Higgs vacuum are the states of the lowest possible energy in some physical theory. And Higgs refers to the fact that if I have some gauge group, then all the gauge fields are zero. Then all the matter fields are at the bottom of some potential, and this is this potential W. And then you mod out by the residual global gauge transformation. This is called the Higgs. Those are the Higgs states. And so this is how X appears. You take the critical loss of some function W, and you mod out by constant gauge transformation. That's what this X is. And while Y is really in some disguise the Coulomb branch of the same theory. So that's the role of X and Y. Now I keep trying to advance the slides here. And the examples of that are Nakajima-Quiver variety. We're a little short on time, but maybe I'll say the following: one representation where the group G is a product of G linear group, and the representation M is the sum of representations of the form I take home. So the product of G VI I take. And as a presentation M, I have a number of copies of home from VI to VJ and VI itself. So then the corresponding, then this homes I index are the way to index how many homes I have is by a quiver. So I have a quiver of the vertices are labeled by the VIs, and the arrows are the homes between VIs. And so this is the corresponding variety is called Nakajima-Quiver variety, since they text by quiver. Quiver is a bunch of arrows, and it means a bunch of dots and a bunch of arrows that lead from one dot to another. So it's called the quiver. So and among the quiver varieties, you can find many remarkable varieties of the world. Like, for instance, you can take the moduli of instantons, or T star of homogeneous spaces, or other things. So and now to connect, so we had to connect X and Y somehow. And I say to connect X and Y somehow. Why had to do with some group and some collection. So maybe to backtrack for a sec. So if I can backtrack for a sec. So Y had to do with some group, and the group had to do with the group G had to do with the fact that I could have some Weyl group symmetry in my torus. So that's how I saw the groups encoded. Anyway, it's a torus, some maybe Weyl group symmetry, and a bunch of hyperplane in the torus, translates of hyperplanes. And now what I would like to do is this right here. This hyperplanes I would like to correspond to the weights of the representation M. Right? So M is some representation of a group. It has some weights, and I'd like this weight to correspond to weights to correspond to hyperplanes and Y. And but then there's a little bit of detail, namely in the formula we had not just gamma functions of monomials and Y, not just kind of weights of the group, but also we had this monomials multiplied by something, like we had gamma q of AI times Y to the lambda I. And so what would the meaning of AI should be is that there is a bigger group of symmetries, namely if I look some representation of my group G, I can look at the normalizer of that representation, some bigger group that acts by automorphisms, and then the weights, and the variables AI and the variables in that bigger group, and this expression AI times y to the lambda I, that is a weight of a bigger group in representation. So this picture here, I would like to correspond to representation where the poles that appear, this AI times y to the lambda I, correspond to the fact that I have, first of all, my group, and y to the lambda I are the weights of some representation of my group, but then AI times y to the lambda I, those correspond to the fact that I have a bigger group, and AI is what sits in the normalizer of my group. And the action will be, all the action will be happening, in fact, in K-theory of X, and the integration, and the integration is like the Weyl integration formula. It's like the standard type of thing. And so this is right. So this is in G, and now there's this. This is going to be slightly technical. So now, if you're going to lose me here, let's I apologize in advance. Is that this is about this interpolation, right? We had to think this G and F are functions that were supposed to solve some interpolation problem. And what is that interpolation problem? I remind you that when in this construction of X, we had to restrict to a stable locus, right? So we take K-theory. If we didn't restrict to the stable locus, if we study the current K-theory of the whole T star M, if we study the current theory of the whole T star M, well, T star M is a vector space. The current K-theory is the same as the current K-theory of a point, and so that's just my group G tilde modular conjugation. But if I restrict to an open set, which is the stable locus, which is what I'm supposed to study, that means I have a map in K-theory from the ambient space to an open. So in K-theory, that map is surjective, and it means dually there's an inclusion. So the K-theory of the stable locus includes as a closed subset into G tilde mod conjugation. Right? And its interpolation problem will be from this closed subset. And this interpolation problem you can set up in K-theory, which you can also parallel interpolation problem in elliptic homology, and this functions alpha to f of alpha and beta to the g of beta. They solve this interpolation problem in K-theory and elliptic homology. That's so maybe I said one more time. We want to solve some solution, some vector space. And then when we solve this, we want to solve it by an integral. And by an integral means we have to go from elements of my vector space to functions on some variables y. Now I'm saying, well, the way my vector space is going to be K-theory of stable locus, it's some fine dimensional thing. And now to go to add this variables y, I say, well, that means this would be a solution of a certain interpolation problem. And what this interpolation problem is, the spec of K-theory of the stable locus is some closed subset in the trivial thing, which is the trivial interesting thing, G tilde mod conjugation, Y alpha and so forth, they're all coordinates in the group G tilde. And when I say, so that means that's the problem we're going to solve. Well, it's time to wrap up. I apologize, and maybe I'll do one example, and then we can talk. Well, then we'll skip a lot of slides and then come to the conclusion. So a kind of sort of baby example. Baby example is the usual univariate polynomial interpolation. If I have a polynomial, I want to interpolate its value is finitely many points. Means I want to extend a function defined on the union where I take product of x minus ai equals 0. I'd like a function extend from that to the whole space of x with coordinate x and ai. Well, this is kind of schematic picture. It's not like, I mean, here I just say that this is this will come back to a more realistic picture. This is more say that you should think of this AIs not just as some points, but also maybe AIs are parameters, means these points themselves are allowed to move. And so that means you have an extension problem from equation defined by product of x minus AI equals 0. You'd like the all values of x and AI, and then in the if I now assume all the variables are invertible, and in fact, you know, I denote inverse of x by y, then my equation becomes this. But this equation is it's exactly the equation for the K-theory of projective space, where A1 through n is the torus that acts on my ambient. So if I have a n-1 dimensional projective space, which is unfortunately here's I see a typo. It should be the capital N should be the usual n. So I have a n-1 dimensional projective space, then I have an action of a torus with matrix element A1 through n, and that the equation for the equivalent K-theory of projective space is that equation. Maybe so. This is maybe a slightly more realistic picture. Is that if I take my space M to be C to the n, and I take my group to be scalar matrices, with the eigenvalue y, then my reduction X as T star of projective space, my group G contains the diagonal matrices, and then the spectrum looks, well, there's a more realistic picture with two A's. This looks like this, and this corresponding equation I'm talking about here will be for n equals 2. There will be the usual hypergeometric equation, and the general case corresponds to this slightly more generalized hypergeometric function. Now I have to somehow wrap up, and not sure what to say. I hope you can read the slides as there's some interpretation for a gamma function in terms of maps to x, and there's some explanation why you should consider maps to x. So this is so there's some. So if you think about how to geometrically get gamma functions, you get geometrically gamma functions by studying maps to vector space. If you study K-theory of maps to vector space, from K-theory of maps from a line to a vector space, then you're gonna get a gamma function. And the way you want to study the way one gonna get in the world of supersymmetric gauge theories, it's good to study. It's very it's interesting to study, and it's important to study maps from some Riemann surfaces to variety X, holomorphic maps, or a K-theory of such maps. And among all of them, so this is this is my favorite transparency. This is my favorite transparency, but this is my favorite slide. But maybe you can read about it later, because from the physical viewpoint, maps to X is just like a weather map. Okay, maybe it's a good thing you can talk about. And and this so now maybe to wrap this things up, most important cases where you study maps from the flat space with the action of Q to X. And if I look at maps from the flat space in which Q acts by rotation, Q was the variable in the Q difference equation that acts by rotations in my flat space, two-dimensional, just in C, Q acts there by rotation. I study maps to X. It's kind of like the analog of Nekrasov function, if you want. So this is, in some sense, the most important case. And this thing on formal geometric grounds solves a certain Q difference equation. So this is where it's, there's some geometric argument to say that this expression here solves a certain Q difference equation. It's a differential Q difference analog of other things that's important in math. And the main result is that, so maybe I'll skip to the main result. There are two of them. There's two of them. First of all, that Q difference equation. If I start with X that corresponds to a certain quiver, that the Q difference equation is the Q difference equation I get are the QKZ and also well, depends on which variables I consider. I have a whole bunch of variables, and some of them is the quantum Knizhnik-Zamolodchikov equation, and some other equation is something called dynamical equation. So you can identify which equations you're solving through this sort of approach. And second is that if I can view this counting of maps to X as a correspondence between X and the stack, meaning I can study maps from C to X, where I fix the boundary conditions at infinity to correspond to a point on X, but I allow the point at the origin to have a singularity and have a map to the stack. So then if I sum over all the maps, I have a correspondence between X and the stack. So I have a map between the K theory of X and the K theory of the stack. And then and in the theorem, main theorem of this talk is that this map with suitable gamma factors is in fact this elliptic stable level, is unique interpolation of certain elliptic functions from a closed subset to the whole thing. So that counting of the maps does solve the interpolation problem. That's the main theorem. And then the formula for the solution, that's a formal consequence of that. And also as a sample application, you also see, for example, the monodrome. Right. I apologize. I've gone over time. Sorry. Can't undo this now. Can't go back in time.
Thanks very much, Andrei. I'll sort of applaud on behalf of everyone who's here. There's a few questions in the Q&A. Maybe you can address them and maybe read out the question.
Right. So Nalini is asking whether there's some connection with isomonodromy problems, like if I want to, and there is. It's but maybe not as direct as I can to be. I don't think I can summarize it in very few words, but there certainly is there's some connection, but maybe it's a subject for a different talk. There's some. So then there another question is there something in terms of solving the equation? Is there something better in the Q difference world than there is the ordinary differential world? Yes, there's tons, and maybe I can illustrate just by the formula behind me. Is that in the Q different worlds? Well, first of all, this Q gamma function, they're actually very nice. As nice function as it can possibly be. I mean, of course, the gamma function is also a nice function, but more importantly, it's only in the Q difference world that I have enough elliptic functions so that I can make this G beta to be to put G beta as a function in the integral and not choose the contour of integration. If I'm in differential case, I can't write a formula like that. That's impossible because I don't have enough constant functions there. There are many things which are much better from both analytic and from both kind of analytic things and simply just kind of the general beauty of math. There's many things that are more non-degenerate in the Q different worlds and do create a sort of headache for in the differential limit. And one of them being is that this formula is written, it makes no sense in the differential world.
So Andrei, maybe I can ask a question as well. You mentioned the sort of a geometric interpretation of the Q gamma function. But is there an obvious geometric interpretation of the beautiful phi basic hypergeometric function you started with?
Right. So this is maybe thanks Jan thanks for this question. So this is maybe if you don't mind, maybe we can go back 1 second, remind you. So what is this function here? So the Q gamma function is given by a product, right? So Q gamma function, we decide it's a product. It's a product of all these terms, and And what is this? It's the if I have a product of 1 minus something, this means I have. It means I'm just considering. Means I'm counting all possible functions on an infinite dimensional vector space. This infinite dimensional vector space is spanned by, well, these are the of where I put 1 minus whatever. Those are the weights of the coordinate on this vector space. Right. So this I need a vector space on which I have some group action on which the coordinates are have this weight x, qx, q square x, and so forth. And such maps is just a space of maps from a line to a line is an infinite dimensional vector space in which if we act by two tora in the source and the target, we're gonna get this is going to, first of all, map of line for line. It's a vector space. It's just polynomials. And if we go and if we act by changes by scaling one coordinate the source and the target, that acts differently on monomials the way it's indicated here. It gives exactly the right way. So if you take trace over functions on the space of maps, then you're gonna get this Q gamma functions. Now going back to, so these are functions from a line to a line. Now we can go function. So we didn't talk about functions from a Riemann surface to some x, but we are going to talk about functions from a line. So here line, as you can see, now function to x. So now this would be just like before, except this will be sum over, when you have maps to x, a maps to x has a topological invariant, namely degree. And so this would be not one product, but rather a sum of things which might have a chance to look as a product. And if we do that sum of things that have a chance to look as a product, then of course we see this. Oh, hold on one second. Then of course we're gonna get this formula. So this formula here, this can be interpreted as you summing over maps now to projective to, well, in this case T star P1. These are the, in some sense, T star P1 is the simplest algebraic variety which can appear in the world of possible x. It's after a line, and if you're doing this kind of map counting to x, we're going to get this hypergeometric function. And then if you do more complicated counting, you're going to get more complicated function. And I was talking, this talk was about these functions.
All right, thanks very much, Andrei. I think if there are no further questions, then I'd like to thank you again for a wonderful talk and for staying, for joining Matrix early in the morning in Melbourne and late in the afternoon in New York. Thanks everyone for attending, and there will be another Matrix online seminar in the beginning of March, so watch out for advertisements for that. Thank you everyone. Bye-bye.
Thank you so much. Thanks.